Okay, so since we finished the proof of Casorati-Weierstrass theorem last time, so now we're gonna start a lemma in this before in this lecture, and then we're gonna talk about the block theorem. So lemma. So I will call it the preparation lemma. Yeah, so this is sorry, this is just my personal preference. So nothing. Yeah, I don't know whether there's another name for this lemma, but let me just call it preparation lemma, or okay, or the preparation lemma. Fine. Okay. All right. So the lemma. So that fd be a function analytic in the disk certain at 0 with radius r, and satisfy the condition so okay. So it satisfies several conditions here. So first, it satisfies the origin is equal to 0. Okay. So keep in mind that the constant coefficient of the Taylor expansion is 0. And then as prime 0 is not equal to 0. Okay. So this implies that the first constant term of Taylor, if the coefficient corresponds to the first derivative, is not 0. Okay. And then the modulus of fg is less than equal to m. In sorry, let me how do I put it? Yeah, so let me just put it here. Sorry for the awkward wording. Okay. Yeah. So basically, as the grounded. So this can tell you a lot by some theorems. So we have discussed. We have discussed several theorems about if a function is bounded, then you can do you can do several things. Okay. Okay. So okay, never mind. Let's continue. So then we set r equal to the modulus of at prime 0, which is the modulus of the constant term over modulus of the coefficient associated with f prime 0 as the second derivative of the first derivative, and then we let rho to be the modulus of f prime 0 square times r squared. Okay. Where this r is like the big radius here, and then over 6m. Okay, remember that this m is like the upper bound. So it's like some little this some multiple of the it's some yeah, it has some it has something to do with the radius and the first derivative, you know, and also like the down over the function. Yeah. Okay. Yeah, I'm not sure whether there's a yeah, yeah, oh, well. Okay. So I'm not sure whether they can do the equation now. Probably there will be, but I'm not sure yet. Okay. So what? So okay. So what's the conclusion? So then, uh, for any arbitrary W naught in this center and zero with radius rho. Okay. And there exists a unique Z naught in this center and zero of radius R such that let's see. Okay, I think you guys can see that. I'll check it later. So, okay, such that yeah. So f and z naught is equal to delta naught. Okay. So basically, like, you pick any. So this is like the special radius, right? Special radius defined by the derivative modulus of derivative square times r square over 6m. Yeah, you can just understand it as a number right now. And then for this radius, so for any point within this disk center radius, there is this unique point Z naught in this disk of radius R, right? So such that f of z is equal to W naught. Okay. So yeah. So we are now. Do we know? Okay. So yeah. So there is a unique Z naught in this disk of radius R. Okay. Okay. All right. So sorry, I'm not so clear about that. So okay. So let me. Okay. Actually, not really so unique. Okay. So let me just continue. Okay. So in other words. So in the disk, in the disk, this radius R, and the hold on. Assume each value. Oh, okay, okay, okay. Okay, I see, okay. Assume, okay. What did you? Okay. Let's see, assumes. Each value whose yeah, so whose okay. Okay. So if there's another value. Okay, yeah, so because this is unique, so therefore if there's another value, okay, so that is it. So yeah, so since this denote is unique, so if there's another value such that yeah, so it kind of so there is two things. So one thing is there is a denote, right, in that. So basically it means that so anything the pre-image is in this set. So so you can say that the pre-image of this one is at least contain this one. Okay. The pre-image of it's contained in that, and then the image of, and then it's unique. Yeah, so namely if another whose modulus is less than rho exactly once. Alright. Okay, so and then the equation and equal to W where modulus W is just simply equal to rho may have no solution. One solution. Or more than one or more than one solution in the disk of potential operating R. Yeah, so so basically so it doesn't say it doesn't say anything about the radius bigger than rho, right? It just says something about the radius. Yeah, it doesn't say anything about the points that are outside this disk, right? It only says things about the point that is inside the disk, such that there is a d naught, such that this d naught is, yeah. Okay, so what's next? Okay, so why, yeah, so why it is true? So, yeah, we are trying to aim to use the short one of I think the Roche theorem. Yeah. So we are aiming to use the Roche theorem. So basically the Roche theorem it produced like two functions and then argue that they have the same number of roots. So here okay, yeah, we are going to use the Roche theorem. So yeah. All right, so let's continue with the proof. So proof. So first, we use the we use the Cauchy's estimate. Okay, so of course. Sorry, I forgot what it's called. Okay, okay. So it's about the first derivative of m. Right, yeah. Okay. So you have a domain that is bounded, and then you have so what do you have? Okay. Okay. So there is some restriction on the image. So yeah. Well, why is that? Why is that zero is okay. Oh, okay, yeah. So, oh yeah, I forgot. What is it like? What is that? All right, so we have okay, okay. I think I quite remember. Yeah. Okay. So, why? Okay. We have that. Okay. So. All right. So, yeah, we have that without calculating. So, okay, so, since So letting R prime approach to R, okay. So again, since, so I prefer to use this. It's arbitrary. So we have, yeah, so why we have that? So since R prime is arbitrary, oh, okay. Yeah, okay. Wait, okay. What? Oh, so for any, sorry, okay, R prime is less than R, right? Uh, why would be, so R prime is less than R, and then, M over R. What is R? Okay, R is something bigger than R prime, okay. And then, Y is M over R. Y is okay. R prime is less than R, right? So, what is it? Oh, okay. So we should have that. And then this is, oh, okay, I see, okay. Yeah, but why? This M over R is what? This M over R, yeah, this M over R is, small, right? This is big, it's small. Okay. But why? Why is less than over R? Because okay. What? Okay. Less than something. Oh. Why am? Oh. Okay. So since this is for any arbitrary R prime, right? So for any arbitrary R prime, we have so so if less than m over r prime for any r type. Okay, so now let is r prime approach to okay approach to this r, right? So why do we have this m prime 0 is less than m prime? So that's an equal. Yeah, so why is that? We let r prime approach to r. Okay, because this is a number, right? So yeah, of course, yeah. So if we let r prime approach to r, then yeah, we let r prime approach to r, and then yeah, it must be less than r. Yeah, otherwise yeah, sorry for the yeah. So it must be less than r. Yeah. All right. Yes. All right. All right. So okay. So yeah. Yeah. So we will continue next time. I have stated theorem and sorry. Yeah. And then I'll start with the calculate estimate. Yeah. So in the next time. Yeah. We'll continue next time.